So what we're going to be looking at now is an overview of electromagnetic induction. And we're just going to give you an overarching framework so that you can pick and put all the pieces together when you're dealing with this topic, which many people find confusing. So very briefly, electromagnetic induction refers to basically how you've got electric, things to do with electricity, and magnetism, and relating it to induction, which basically means is how one induces another. And that relates to the laws that we're going to get to in a moment. But basically, the two things are interlinked, and that gives rise to all other fancy things like your electromagnetic waves and things like that. But we'll leave that aside. And we're going to break it down into a sort of piece by piece thing. So the first thing you need to be aware of is your magnetic flux, and think of it as a change in magnetic flux, which is phi. So if you have a change in magnetic flux, then we'll call that a delta phi. Now, if you have a change in magnetic flux, then we actually have talked to you about what might happen here. If you have a change in magnetic flux, then we have something called Faraday's law, which very simply states that the induced EMF is going to equal, we can ignore the negative for now, but it's related to the change in magnetic flux. So Faraday's law basically says that if you have a change in magnetic flux, there must be a rate of change in that magnetic flux, and that will result in an epsilon, which is EMF, which means you now will have an induced EMF, which you can, for our intents and purposes, think of that as voltage. Okay. So if you have a change in the magnetic flux, you end up with an induced voltage according to Faraday's law. Nice and simple. Faraday's law is very important. We're not going to cover that in detail now. It's just part of the overview. Now, you now have an induced EMF, which is a voltage, which means you now have a voltage in something that is a conductor. And this something doesn't have a battery, but it does have a voltage. Now, depending on your conductor, and it really does depend, but it could be possible that this conductor is closed. So if you have a closed loop, you therefore have a closed circuit. And so you might know from your previous work in year 11 that, hey, if we have a loop, if we have a loop and there is a voltage across that loop, then basically think of it as there is a battery, imaginary battery there. There isn't really a battery, but there's a voltage. So it just means that this loop will now have a current flowing through it. But of course, there's no actual battery in there. There's just a voltage that was induced. So we will call this an induced current. So this induced current only occurs if, of course, there is an induced voltage and if the loop is closed. If the loop is not closed and there's a break in the loop, as you might sometimes have, then there's going to just stop everything and there's not going to be any induced current. There will be an induced voltage, but there will be no induced current. Kind of like how just because there's a voltage doesn't mean there's always a current. Kind of like a battery has a voltage, but unless you connect it up, no current is going to flow. So we now have an induced current, which for all intents and purposes is, well, it's basically a current. It's a current I. Now, later on, we might talk about things like eddy currents and induced currents and how we might use them. So keep all of this in mind when we talk about the later things. But for now, just think of it as you have a current, which really is what it is. But this current as you should well know, all currents in wires will create a magnetic field. So we have the discovery by Orsted, and sometimes referred to as Ampere's law. But the idea is, if you have a current, whether it's an induced current or not is besides the point. If you have a current, then that current will create a magnetic field. Right? We've revised this before. It will create a magnetic field whose direction is basically going to be indicated by the right-hand grip rule. And it's got a magnitude which depends on the distance and the k here, which is mu naught over 2 pi. And they can work out the magnetic field created by this particular current. And a magnetic field, I guess, because, well, it's intimately linked with magnetic flux, will, of course, affect magnetic flux. And we know that, quite obviously, because flux is equal to BA. So if you're going to create a B, and there's some sort of area, and there's no reason why there's no area. If there was area before, there still is area now. This will clearly influence the changing magnetic flux, which now means that your electromagnetic induction is talking about this kind of general loop situation where basically over here, you can see that a change in your magnetic flux, so magnets, results in an EMF, which is voltage, which is electricity, right? So you get to the situation where a change in a magnetic field / flux results in a change in electricity. And over here, because you end up having something in the electricity changing from nothing to something, you end up creating a magnetic field. So basically, magnetism affects electricity, and your electricity or moving electrostatics affects magnetism. And so they influence each other. And this interplay is what we're going to be talking about. Now, just like there's eddy currents here, we should also note that induced EMF is also basically just voltage for all intents and purposes. And so we'll be looking at that in the context of back EMF, for example, and a few other things when we get to that. But for now, recognize that there's sort of this interplay. One affects the other, and these are all your laws from, well, basically the late 19th century, which we'll also look at in a bit more detail in module 7 when we talk about electromagnetic waves again. But for now, I want to now focus on this part over here, this link from the magnetic field back into the change in flux. So think about the loop. You had a change in flux. So let's say the magnetic flux went up. Then Faraday's law says you're going to get an EMF. Ignore the negative for now. You're going to get an EMF, which will then create a magnetic, which will create a current if the loop is closed, which will then create a magnetic field, which will then change the flux again. Now, the magnetic flux or the magnetic field can change the magnetic flux in one or two ways. It can either increase the magnetic flux, so it will increase the change, or it could kind of go against it and decrease the change. And if you think about this, if you have one change, so if this goes up and you go around the circle and you make it go up even more, that means you're going to go around the circle again and make it go up even more and even more and even more and even more, which means that any change in the magnetic flux will result in a bigger voltage, which will result in a bigger current, which will then loop around and or make yourself bigger again. You're going to have this positive feedback loop, which goes around an infinite number of times, giving you an infinitely large change in magnetic flux, giving you an infinitely large voltage and infinite current, all from any possible change. And that, unfortunately, to our great disappointment, violates the conservation of energy. Which means, I mean, if it was true, it's great. You just get any change and, well, you'll get infinite voltage and infinite current, so you'll get infinite energy, and we have no issues with energy anymore. You don't need nuclear fusion, you just need a tiny magnet. Unfortunately, that's not real life. So that means there's something wrong with this picture. And that basically means, unfortunately, when you loop around, the magnetic field that you get here does not increase the changing magnetic flux, but rather it brings it down. It goes against it. So what that means is that the magnetic field that's created by this induced current, which is created by this induced EMF, must oppose the change in magnetic flux that gave rise to them initially. And that is the next law that we'll talk about in a bit more detail. But basically, that here is Lenz's law, which basically is all about direction. So you have Lenz's law, which simply states that the induced current must flow in such a way such that the magnetic field created opposes the original change in flux. And that is why you now have a negative feedback loop. So when you go around the loop, this will now fight against it, and then you will basically reach an equilibrium. So it's kind of like Lester's principle in chemistry, if you do that. So basically, or it's like friction in physics, where you want to go to the right, but it will push against you. So instead of pushing to the right and things getting just faster and faster forever, there is some counterbalancing force, if you like. So that's Lenz's law. And that explains this negative here. This negative that is in your reference sheet for Faraday's law is really in reference to Lenz's law, which is really referring to the direction of the induced current. We'll do more practice on Lenz's law, and we'll do more questions on it, and we'll do more explanation on that. But this is a good overview of all the elements of electromagnetic induction to make sure that you get an idea of where everything fits, because basically there's a lot of aspects to it and they all relate to each other. And a lot of the time, students get confused about what's what and how they relate to each other. So this should give you a good idea of where things fit, so that when we're talking about particular aspects, you know where it is in the general picture. And that should help you a lot with this particular topic. If you know how electromagnetic induction works, then you should be fine with the topic and you can apply them generally. And that's how you do it.